So this is chemistry that I actually kind of like. This is looking at our enolates again, and now we're going to look at them as how they can react with each other. So this summary slide, forgive me, I don't think I actually put at the very beginning, but it is here, and unfortunately it also has a bunch of stuff that we don't need, at least yet. So this stuff in this corner we can get rid of because that's officially the next unit. I believe that's going to be chapter 20. That part of that reaction we can ignore, including that part. Up here, we can ignore that corner. And then all of the rest of these, which really isn't all that much, is stuff that we're going to be responsible for in this unit. The first part's right out here, and this, and up here is just kind of a special case of that same reaction. Were already covered when we talked about enolates. Theoretically, they were supposed to have occurred in Unit 1, but we ran out of time, so I bumped those into the beginning of Unit 2. So we're going to go back and look at the value of those enolate reactions, and that's kind of where the heart of this chemistry is sitting right in here, and how we go back and forth between it. The primary focus is going to be on the enolate side of it, okay, just so that you're aware, because it helps to drive the reaction a little bit better that way. So that said, let's go ahead and kind of do a brief walkthrough of the overall mechanism. So if we look at our standard format, so we can think about how this was kind of discovered potentially, we start with an aldehyde. Okay, so there's our aldehyde, and we picked a relatively simple aldehyde, just acetaldehyde. So we have those 3 hydrogens, and then we have, that one is a unique hydrogen, 2 carbons, and the oxygen. We throw in a decently strong base, our ethoxide. That ethoxide is going to act as a base and remove the most acidic hydrogen. And so what we talked about back in the enolate is it's going to remove one of the red hydrogens. The blue hydrogens should not get removed because they aren't particularly acidic. Okay? There's nothing we can do to stabilize that. The red ones are acidic, even though they're further from that oxygen, because the charge that we produce, that negative charge on that carbon, can be resonance stabilized. So this resonance stabilization comes in again and helps us kind of process through that reaction. But if that's it, that's it. Like, where else do we go? And so there's another arrow here, and that's where the aldol kind of steps in, is that there is more that can happen. Okay? And a lot of that is due to a mixture of kind of 2 things. First and foremost, the base that we used isn't a stupidly strong base, it's just a strong base. Okay? And that's going to become important because if we look at that first step is not unidirectional. It's actually in an equilibrium that is actually probably going to favor reactants over products. And that becomes important because what that means is that while, yes, I can form some of this enolate, I will also have in solution unreacted aldehyde just chilling out. And why does that become important? Well, the enolate is great, negative charge, we've got a nucleophile. Well, and as we just addressed within this particular unit, the carbonyl, as far as its chemistry, is pretty fantastic because that carbon is a really good electrophile. And given the proper circumstances we'll dig into in a little bit, that nucleophile can attack that electrophile. Okay? So I'm just going to clear it all and redraw. Here's our aldehyde. And if we had our, nucleophile come in and attack, we would break the pi bond, and the resulting structure, and because that box is kind of in the way, I'll draw it a little bit further over. The resulting structure is going to look something like this. Red bond to show our connection. And actually, I'm going to show that new bond in blue There's the carbon of our carbonyl that we just attacked, negative, and then there's the remaining carbon. So you note that I swapped those two pieces. Okay? Why? Just to show a slightly better alignment of those structures. And what we've now done is that nucleophilic addition from the enolate to our unreacted aldehyde. Okay? And we've now done that first step. Yes, that gives us a negatively charged species, which is not particularly stable, but again, remember, if we're going to see an ethoxide like this in base, we also have a solvent of the ethanol. And yes, we should be better about always specifying that that solvent is there, but it very often just comes implied. Okay, why is that helpful for us? Well, if we drew that in as a solvent, we could now have that negative react, and we would now protonate it, and we would end with our final structure here. Okay? And why does this become important? Well, this structure gives us why the name of the reaction. The name of the reaction was an aldol reaction. So if we break that down, we have ald from aldehyde, and we have all from our alcohol. And admittedly, I didn't draw that out very well, but if we look, there's an aldehyde and an alcohol. Right? That's the origin of this whole process. Okay? Is that if I take an aldehyde and I put it in a slightly basic environment, it's going to push to this product where it is it dimerized? I think it does qualify as dimerized, and those two pieces then form a new connection, and we get this new product. That's the point, or the name, or origin of aldol, which is kind of cool. This works for virtually any carbonyl-containing functional group. Aldehyde, ketone. Those are the big ones right now. Why? That's what we're looking at. As soon as we move into chapter 20 and 21, we get effectively identical chemistry with the ester, amides, and acids. Okay? Those reactions we need to be aware of because they do kind of still pop up, though to much lesser extents, and we'll discuss that when we move there. Okay? So we could do this with a ketone just as easily as with an aldehyde. Yes, it gets a little bit more complicated, but we will see that in a second. But if you're looking carefully, there is another box here, okay? And it is, let's see, cool. The aldol reaction rarely stops at just the aldol. Okay? It almost always continues through some secondary chemistry. And that secondary chemistry is a condensation reaction, also known as an elimination. Condensation is because when we run the reaction, we see the formation of water condensing on our equipment. Right? That's the name condensation. Well, the water had to be eliminated from the structure. The elimination is the better name for this. Okay, so where is that coming from and why? Well, one of the big pieces of information that can help us with that is elimination. And if we remember all the way back from first semester, to really push an elimination reaction, one of our characteristics is the presence of a strong base. Wait a second. The lovely face there, Mike. Strong base. We're in a strongly basic environment. So yeah, elimination is a high probability here. So the question becomes is where is that elimination happening? Right? Well, the condensation gave away a hint. We need water. So to do that, I need an oxygen. So look at the aldol. Where is there an oxygen that is closest to becoming water? Hopefully you see that OH is probably our best bet, right? But it would need another hydrogen. So I could put another hydrogen on it and then I'd be positive, right? And then water could leave. And not so much. And then not so much because basic environment. I can't protonate that water to have it leave, okay? So what could I do to help get that oxygen to leave the structure and then maybe later pick up a hydrogen? Right? Well, something would have to force it off. If I used the ethoxide, that could nucleophilic attack and push that off, but that's not productive, and that's not really doing an elimination. That would be doing a substitution. To do the elimination, I would need to remove an alpha hydrogen. An alpha hydrogen would be at either, that's blue, or that's supposed to be an alpha, or purple. Okay? There are hydrogens located at those positions. Which hydrogen should I remove? Well, if I remove the blue hydrogen, what do I get? The electrons could come over, we would form a pi bond. We would eliminate ROH. And we didn't do anything to the other side. If we did the purple one, what would we get? Well, those electrons could come up, kick that out, and we would end with this structure. Well, which one is a better product, the purple or the blue? Hopefully you can see that the purple one makes a lot more sense as a stable product because we have a more substituted pi bond, and probably the more relevant piece of information, that pi bond is conjugated. That conjugation vastly increases the stability of that final product, making that last step of the reaction incredibly product favored. And that's why our aldols almost always undergo this secondary reaction, because we end up making a much more stable product than what we started with. Okay? And that's due to that internal conjugation. The blue one really isn't more stable. If anything, it's less stable than our starting material, so the blue one doesn't make sense. Somebody might be thinking through the back of their head, but hey, you eliminated hydroxide, OH minus. Isn't that a bad leaving group? Yes, it is a bad leaving group, but it's leaving into an environment of effectively hydroxide. So again, that comes out as a wash, and really what we're relying on is the stability of the organic molecule to drive this reaction. Okay? So the aldol reaction on its own, if it stops at the aldol, it's usually not to very large amounts. We don't get a lot of product. It's when it does the aldol condensation and we finalize that we actually get an extensive amount of product. Okay? And what's really going to drive that, or kind of push that, is that if we look at that purple hydrogen is actually more basic than the hydrogen we removed all the way back at the beginning. Okay? Why? Well, the purple hydrogen at the end here has two electron withdrawing effects. We have the two oxygens connected, both withdrawing electron density. So due to induction, that purple hydrogen becomes more basic. It is more likely to be removed by our base solution than our starting aldehyde hydrogen structure, and yet more evidence to push us towards this aldol product. Okay? So it's a really kind of neat reaction, and all we're doing is following some kind of basic patterns that we've already established. We're just kind of connecting all the dots. There are all sorts of potential complications that can come with this reaction. And really, instead of me pointing those out, what I would like you to do is to go through and take a look at these practice questions and decide what should your product be. So attempt to run the aldol and see what you would get. See how it comes out. Okay? This is, again, a really good opportunity to pause, and it is such a good opportunity. I'm going to throw some questions at you. Okay? So let's go ahead and start this off. Okay? It's always nice to have someone smiling at you, right? There we go. Cool. Let's take a look at the very first reaction. Okay? When we run this reaction, our base comes in, removes the hydrogen, and we would create our nucleophile at that position. That nucleophile could now attack a second equivalent of our aldehyde. So, and we can now try and connect those structures together. So we've got our black structure, aldehyde. The new bond connecting out to our oxygen, hydrogen, and the ring, that would be negatively charged. That could pick up a hydrogen. And we now have an aldol. Should this one also do the condensation? Okay. To do that condensation, what did we need? We needed another acidic hydrogen. Okay. Well, I do see that red hydrogen floating out there. Is that one particularly acidic? Okay. Is there any way to stabilize that hydrogen? If we go backwards and look at the hydrogen that we removed a hydrogen from this position. There's no other hydrogen there, which means we can't do the condensation. We are stuck at the aldol product. Okay, so that would then be our answer. Typically, you probably wouldn't see the hydrogen in there, and we could have this as an end result. You would probably also see a multiple choice answer with the double bond in there, which would exceed octets, but that would trap the people that are just trying to memorize the result as opposed to trying to process through the steps. Okay? What happens with the next one? Well, remember, we've got an aldehyde, so, let's just cheat. Let's use a cheat here. We've got our ring. We've got the aldehyde, and what we could do is we delete that and we draw in the other half. Okay? And I haven't discussed the cheat yet. We'll see that actually with our third example. Okay, well, there's the product. Well, hold up. Step one of our mechanism is remove the acidic hydrogen. The acidic hydrogen is the enolate hydrogen. There needs to be a hydrogen there. I just drew it in so that we could see that spot. Is there actually a hydrogen there? No. Okay, that would exceed the octet. Step one of the reaction, that acid-base step, the formation of the enolate, doesn't happen. I don't get it. Okay? If I don't form the nucleophile, then I can't run the reaction. And so that kind of cheat of trying to jam together the structures ends up backfiring on you because, well, the chemistry wasn't there. So be careful using kind of cheats as you approach these questions. Okay? So let's see how the cheat could be used appropriately. We've got our base. We do have our hydrogens. Okay? Note that this one's a little bit different than our very first question up here, because in the first question we only had one hydrogen. Okay? So with this one, we now have two hydrogens, which means the condensation probably makes sense. So let's set up the cheat. First thing I want to do is I want to make the enolate. Okay, so the enolate I'm going to put as my nucleophile. I'm going to default this on top. Okay, and the reason being is that my nucleophilic carbon is right there, and that kind of points downwards. Well, what do I want to have it point to? I want to have it point to my electrophile, okay, the carbon of my carbonyl. Now I can go through and draw in the extra pieces, 1, 2, 3 carbons total. So I've got 1, 2, 3 carbons. Now what happens for my cheat? The nucleophile attacks. I break one bond. Okay, because I still have hydrogens there, I can do an elimination and I break the other bond. I now have the final product. Okay, yes, that looks awful. So you could permutate this or switch this around. 1, 2, 3, 4, 5. So I'm looking for the longest carbon chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The fifth position, well, first position should be the aldehyde. At the second position, I continue with my double bond. So there's, whoops, make that a little cleaner. There's my double bond. I also have that methyl group. Okay. And then there's the 1, 2, 3 of that second structure. I could indeed draw on the hydrogen if I so felt. Okay. But I don't need to, and this would be very likely a way your final product could show up on a multiple choice test. So cool, the cheat is really just stack them and start erasing stuff in between. That works out really, really nicely. Okay, so now let's move to the next one. Okay, I'm going to erase all those because you already discovered the answer to all those. So since you've already got that written out, we don't need to see them. And we look at this one. Why is this one different? Well, this one is different because I don't have the same aldehyde. I have two different ones. So this is now referencing a crossed aldol. Exact same chemistry, but because I've now switched the identity of one of my materials, it changes the name of the reaction, which I think is a bit silly, but that's what they do. Okay, so what we do have to identify, though, is which ones are nucleophile, which ones are electrophile. As we already addressed earlier, this structure can only act as an electrophile. There is no alpha hydrogen to do the activation of the enolate. So I could draw it in this fashion, drawing it at the bottom half of this. That means this one must be my nucleophile, so I'm going to draw that out where my nucleophilic carbon is kind of right above the carbonyl. Okay, that nucleophilic carbon has two hydrogens, which means I can do the condensation. Delete that out. Done. God, isn't that nice? And when it all just comes together and it's beautiful and it's easy. Okay. Now it's getting really, really crowded here at the bottom, so I'm going to have to delete that. We're going to keep the quote-unquote cheat visible. I'm going to delete some of these things so we don't have to look at those. We'll delete this one, and we'll bring in the next one. Okay, cool. So it's another crossed aldol. Okay, so now let's go through the same thing we did with the last one. We have to identify the nucleophile, identify the electrophile. Okay, so the nucleophile is the one with alpha hydrogens. Well, dude, alpha hydrogens. So this must be the nucleophile, which means this one must be the electrophile. Which is true, except that second one also has alpha hydrogens, which means it's a nucleophile, and this one is an electrophile. What does that mean? Which reaction happens? All the reactions. That sucks. Okay? We will get the product of those two combining. We will get the product of these two combining. Okay? We also, by drawing this out, should notice there's another product. There's one here, and there's one here. This reaction, as it's set up, is going to produce 4 products. Okay? So synthetically, this is a crap reaction to run because the best I could hope for a yield is going to be a 25% yield of my target compound. So this is a mess. This was poorly designed, okay? And we don't want to do this. So how could we synthetically fix this? Okay, well, the previous question did address some of that. Okay, the previous question pretty much went through and said, well, I'm going to get rid of all those hydrogens there and put in the benzene ring. Okay? By doing so, that one can't act as a nucleophile. And I've now limited that reaction. Okay? And with the last one, we really just talked about the nucleophile electrophile here. We didn't actually address that we also had a second product. Okay? So again, we go back to the question, how can we fix this issue? Okay? So one way was limiting the alpha hydrogens for one of the positions. The other way is going to be getting a little bit more nuanced and controlled about the base that you use and when you use it. If I mix the base with this species first, that should make the nucleophile. Okay? And I should have very little of this one coming in as a nucleophile. So if I split up the steps, I can start to limit some of those pieces. However, that base being a not stupidly strong base means I'm also going to get some electrophile from that starting material. Okay? So I have to consider not just the sequence in which I mix these things, but I also have to consider the bases that I'm using to complete the reaction. Okay, so what do we mean by that? Let's take a look at the reaction underneath. Okay, what did the reaction underneath attempt to do? It's the exact same materials, but we're now mixing this base only with this one. That should produce a larger percentage of this nucleophile, which then means it could attack with that electrophile. And this species comes in solely as an electrophile. Okay? That would work, except that this base isn't stupid strong. Okay, not stupid strong. What does that mean? That means that base will come through and yes, produce some of that nucleophile, but it will also keep some of that starting aldehyde around. That starting aldehyde could react with this to give us a second product. So dang, splitting up the steps helped, but it didn't fix everything. Okay, so how else could we go through and do it? Okay, while I'm frantically erasing out here, you should, in theory, already have the potential answer to that, which was the last reaction. How does this last reaction solve that? When we go through and take a look, sodium hydride is a stupid strong base, so what it will do is convert all of this material into the corresponding enolate. For those of you saying, isn't there still a carbonyl left? Okay. Couldn't I have had this attack here? No, this negative blocks that reaction. So once you've converted it across to the enolate, you've destroyed the nucleophilic or the electrophilic characteristics of it. Sodium hydride, being a stupidly strong base, does not allow the reverse reaction. It converts everything across to the nucleophile. Now that nucleophile can react with the electrophile in a second step. This cleans everything up and I get one product. Right? So we'll go ahead and delete everything, show all the reactions again. You should be able to potentially pause the video again, double back through, and see if you can resolve these things addressing the issues that I've pointed out. You should be able to draw each and every single one of those products. Okay? So, lessons from that. You need alpha hydrogens. Alpha hydrogens are critical to this reaction. Why? They're the enolate. That's what drives this reaction. So that first reaction didn't work because it didn't have the alpha hydrogen. Okay? Crossed aldols, when we're mixing different aldehydes with each other, these have really big control issues. And so we have to be a lot more kind of careful with how we organize it. Okay? One way to do it is kind of a reagent control, or that's what I'm calling it, a reagent control. You make sure only one of the reagents has alpha hydrogens. That cleans up a lot of your issues. Okay? If you can't do that, then you have to come up with other methods. Those other methods, stepwising the reaction, splitting it into two pieces as opposed to one pot, okay? Or changing the base, which would be our base control, to ensure that we only get one enolate. Right? And that is a challenge to do. But that's kind of all of our big pieces. 30 minutes of a video on enolates. And if you're looking at this, you're like, well, dang, this sounds good. Except we're not done with the video. Are there more issues that could pop up with bases? Ketones also have alpha hydrogens. Okay? The problem with ketones is that they have two different alpha hydrogens. Which one do you remove depends on the base. Okay? So for instance, if we take a look at this structure, we have 3 alpha hydrogens out here, and we have 2 alpha hydrogens in here. If I was to go through and make an enolate using these individual bases, T-butoxide removes the blue hydrogens. LDA removes the red hydrogen. Sodium hydride removes the red hydrogen. So there is an effect based off of the base. How could we possibly predict that? And that's a genuine question that is kinetics and thermodynamics. Right? Sodium hydride and LDA are stupidly strong bases. They're going to try and neutralize as fast as humanly possible. What is most accessible? Okay? The blue hydrogens or our red hydrogens? I switched the coloring, didn't I? Well, I'm going to have to switch the coloring because of the words down below. Which hydrogens are most accessible? The blue ones or the red ones? The blue ones are most accessible. These species, being stupidly strong, are trying to react and cancel out as insanely fast as possible, which means that they will target that blue hydrogen. Okay? The other one, our T-butoxide, is still going to target or react with the blue hydrogen because it's the fastest. Right? It is the kinetic product. But that step becomes reversible with that one because when we go through and remove those hydrogens, we're talking about forming the enolate with the double bond external to the structure, or we're talking about forming, I should color code that, or we're talking about the enolate with the double bond internal to the structure. The difference in energy is that the red one is more stable. Therefore, if we have a slower reaction or a larger equilibrium, because we're looking at O minus versus O minus, we're going to drive to the thermodynamic, the most stable product. If that reaction can't run in equilibrium, sodium hydride and LDA, we only form that external double bond, which means our enolate chemistry is driven to those individual alpha positions. Okay, so we need to keep that in mind when we're going through and running our aldol type reactions. For the record, aldol says aldehyde, not ketone. Okay? There is the equivalent in ketones. In fact, I think they actually call them ketols. It's the same thing. Okay? We don't need a new name. You're looking at a carbonyl with alpha hydrogens forming an enolate. That enolate can now react. Be it a ketone, be it an aldehyde, be it an ester. Okay? That chemistry is still all there. Okay? So you have to be kind of cognizant of that. The last kind of piece we'll throw into this is that this can happen in an intramolecular type fashion. So far, we had our two carbonyls, the one forming the nucleophile and the one forming the electrophile, as separate molecules. They don't have to be separate. They could be connected. Okay? And as soon as they connect, now there's lots of opportunities for where you could be forming the nucleophile or electrophile. Okay? So when we look at this particular reagent, there's lots of alpha hydrogens. Well, which alpha hydrogen gets removed to form the nucleophile that can then react with the other carbonyl as the electrophile? Okay, so how that ultimately gets decided is a little bit to do with the base strength, but it is actually driven a lot more based off of the product formed. This product, if we go through and look at this, we removed the alpha hydrogen from here and then attacked, arrow got a bit sloppy, and then attacked that carbonyl. Okay? We could have just as easily grabbed this one and attacked that one, but they're equivalent, right? Okay? So why did we do that? Why did we not take these alpha hydrogens and attack there? Okay? What's the difference between the purple one versus the red one? That's a good question. Draw the purple product. What would that product look like? Okay, 1, 2, 3, 4 atoms need to be connected. That would be a ring. Okay, helps if I label them 1, 2, 3, 4. Helps if we actually go and sequence, dude, because that's how we count. 1, 2, 3, 4. 1, 2, 3, 4. Okay, at position 1, we have that extra carbon with the carbonyl. At position 4, we have that methyl, and we have now the oxygen, okay? Our connection or our alpha hydrogens are, at 4. Helps if you can count. Man, made the same mistake twice, okay? Do we still have acidic hydrogens at position 1? Yes, so we could eliminate, and we would end up with this as a product. Okay? If we wanted to go a little bit better with our geometries, there's our geometries. So again, which product should we get? Should we get that purple one or the pretty nice looking drawn one? And then why? Okay? Why? Hopefully that's somewhat obvious. You're looking at forming a 5 or 6 membered ring. Why form a 5 or 6 membered ring? Pull back the dredges of memory from OChem 1. 5 and 6 membered rings are the most stable ring. That's why they're allowed to form. Okay? And if we're going to attempt to form a 3, 4, 7, or 8 membered ring, those have too much strain associated with being able to, either too much strain in the 3 and 4 end, or the 7 and 8 end, they're too far away with the odds to actually link back. 5 and 6 is our sweet spot to allow that formation. Okay? And that's really what's happening behind that. Okay? I think that is actually the end of this. Look at that, a white screen, that's always good. And so that's the end of our aldol discussion. We will see some more types of reactions involving the aldols and kind of layering now all of this information, because we're going to go back to our conjugated alpha beta unsaturated carbonyls. Okay, so thanks for listening. You did a great job moving through this one, because that was an interesting, challenging one. Stop is on the other screen.